Segment of PA4 videos, we are going to walk through the code and try to understand what each part of the given code does. So the place to start would be maximum entropy classifier factory, whose job is to train a maximum entropy classifier and return it given the training data. So the training data is a list of labeled datums. Labeled datums are nothing but a list of features of the type F and a label of the type L. The probabilistic classifier that we are going to return would also have these parameters template parameters F and L, and essentially maximum entropy classifier implements the interface defined by the probabilistic classifier. So going in, we see that we have a function called build encoding given the training data. Now what does this do? Let's go to encoding and try to figure it out. So it says that it maintains the correspondences between various representation of data, label and features. The external representations may be object based, but we translate them to integers. And let's look at an example now. So let's say we have these features on the left and the label on the right. Each row is a training instance. Note that the features are essentially indicator features. So if we say left form press, it means that this feature is present, and only those features which are represented in this list are the ones which are present. So this is a sparse representation of features. Now we do the encoding. So encoding is very simple. Essentially we map each feature to a unique number. So press gets the index 1, cpos tag noun gets the index 2. Now we see press again, it does not get a new index, it is simply mapped to the old index. So now we have a set of features. The set has unique features and each one of them is given an index. Similarly, we do it for the labels. Now we replace the features and the label, which were strings in our case, or a list of strings and string in our case, with integers. And this is essentially what the encoded data looks like. Note here that we have 1, 1, 2, 1 and so on. So the first element of the tuple represents the index of the feature that we are representing, and the second element represents the count. If we go back, we see that the same feature appears twice for the purposes of illustration, and then we have a count of 2 for the feature represented by left cpos tag verb. Now let's go back to the code. So here we have encoding, which essentially tells you which feature is at which ID, which label is at which ID, and it maintains the two-way mapping. So going further, we have build index linearizer given the encoding. The encoding is essentially the lower half here, not the data, and we want to have a index linearizer. Now what does index linearizer mean? Note that we need parameters which are representative of a feature as well as a label. So for example, if we have a class 1, we need a set of parameters which represent all the features. We need this set of parameters for each label. On the other hand, if you look at it the other way, for each feature we have a parameter corresponding to each label. So this is a feature label space. What index linearizer essentially does is that given a feature and a label, it returns the corresponding parameter. So that is the job of an index linearizer. It linearizes this 2D array of parameters into a single long vector. Build initial weights essentially takes this index linearizer and returns a set of zeros, returns an array of zeros. Now we have this function called encode data. Encode data, given the training data and encoding, essentially does what we are doing from this step here to this step here. It encodes each of the features and the label with the corresponding indices and maintains the count. Then we have the max end objective function, which is being called from here. This takes in the parameters encoding, data, index linearizer, and sigma. Note that the sigma is the same as the smoothing constant, which were introduced during the class lectures. Now let's take a look at max and objective function and see what we have to do there. So here we have index linearizer, encoding, and data, which get initialized with the constructor. What we need to implement is the calculate function, which, given the array of weights, it calculates the value of the objective function and derivative for each parameter. Now you must be thinking that the weights are should be a 2D array for a max and classifier, but remember that we had an index linearizer in between, and it linearized this 2D array of weights into a single long one-dimensional vector. Similarly, the derivatives, we have a derivative for each weight, and these derivatives will also be in the form of a single long vector. Now let's say you want to, in the process of calculating the objective function and the gradient, you want to access a particular weight or a particular parameter. So how do you do that? Let's say you have an instance, let's say you have the first instance in this data set. So we have the label 1 and we have the features 1 and 2. So for this particular instance, since it's a sparse representation, we should make use of its sparsity and only deal with the weights which correspond to the features 1 and 2. To do so, we need to look at the class index linearizer and see how we get that. So get linear index essentially transforms the 2D like the 2D coordinates into the single coordinate, and given the feature index and the label, so here the feature index would be, let's say, 1 and the label would be 1. It gives the position of that parameter in the one-dimensional vector. This transformation is simple, and if you take a look at it, you would be able to understand it. So given a linear index, we can get the feature index back and also the label index back. So this is a two-way transformation that index linearizer provides us. Now that we have looked at maximum entropy classifier factory, we need to look at the maximum entropy classifier. This essentially is given the trained weights, and its job is to calculate the probabilities. Your job is to implement the function getLog probabilities, which would give you the log probabilities for each class given a particular data instance. Index linearizer.num labels essentially is the number of classes. This function is utilized by other functions like get probabilities and get log probabilities, which instead of returning something like this returns a counter of type L. Then now that we are done looking at maximum entropy classifier and related things, let's look at the dependency parser. Specifically start with the dependency parser tester. So these are the options that can be provided along with on the command line. So we have the train path, test path, parser. This refers to the particular class which we'll be using as the parser. Then we also have the option of it being typed or untyped, and also training on a smaller subset of sentences. So this essentially starts by reading data. Let's look at read data. So read data is a function of Cornell reader. Cornell reader essentially takes in the path and whether the data set that we are looking at should be labeled or not. If it should be labeled, then it retains the dependency relation. If not, it simply replaces it by an empty string. The parsing is done in the class token annotation, which given a line and whether the fact that it should be that we have to extract labeled dependencies or not, essentially captures the features and the label along with the ID. Note that the token annotation is for each token. So a sentence is represented by a list of token annotations. When we talk about features, we are looking at the features given by universal dependencies dataset, which are form, lemma, pos tag, cpos tag. So note that pos tag and cpos tag have been recently relabeled to be xpos tag, upos tag and xpos tag respectively. And there are also other features which are given and some miscellaneous text if there is any. The label is essentially for a given token, its head and the dependency relation with that head. We shall use these two classes, token features and token label, to train and evaluate our parsers. Token label, you can see that if it's not passed the dependency relation, it assumes the dependency relation to be an empty string. Now moving on to the dependency parser itself. This is a interface which requires you to implement the methods train and parse. The method train takes a list of training sentences. Note that list of token annotations is essentially a sentence, and the function parse takes in a sentence which is a list of token features and returns a collection of token labels. Note the distinction between the usage of token annotation, token label and token features. For training we need label as well as the features, and for parsing, however, given the features we should be able to return the label. Now let's look at the class arc-eager-parser. So we have already seen the task of train and parse. These are the functions that need to be necessarily implemented. We have also given us some scaffolding code to help you start thinking about what you should be doing. So if you've already looked at the other video which explains the oracle, we have a function corresponding to that, which is the extract labeled datum. So given a sentence, it extracts the labeled data. Let's look at some other members of this class. So we have the parser action, which is essentially an enumeration of the 4 parser actions that we are required to implement: left arc, right arc, reduce, and shift. Then we have a class called parser snapshot, which is essentially representing the configuration, and in that we have already provided stack, buffer, sentence, and dependencies. Note that dependencies is a map from integer to token label. Here the integer would be the index of a particular word inside that sentence, represented by id in token annotation, the same id as this. And token label essentially represents the head and the dependency relation corresponding to that. We have a few functions which we have which you might want to implement. The parser snapshot is simply a constructor which takes in a sentence and constructs a parser snapshot. Can apply action, it looks at the current configuration and given a particular action tells you whether the current action can be applied or not. This should be useful for you to see whether a particular action is legal in the current snapshot. Apply labeled action takes in a snapshot, an action, and a dependency relation, and modifies the current snapshot to faithfully represent what would happen to the snapshot had the action been applied to it, once the action is applied to it. Now, for every configuration, we need to be able to extract features out of it, which is what this function extract features does. In the scaffolding code that we have given you, we simply represent features as strings, and we also represent the action to be taken as a string. Note that you can have any other data structure that you want. You're not required to use the scaffolding code. This extract label data function I've already explained to you. It's basically doing the job of the oracle that as we explained in the other video for this assignment. And we also have 2 functions to help you out debug the particular part of the code. So we have check label extraction, which you can use to see if the extracted labels given a sentence look correct. You can call this class arc-eager-parser.java from the command line, and it would read from the training dataset, and for the first 10 sentences extract the labels and print them out for you. That is more or less what you need to know about the assignment regards to the code. You also have the file numerical gradient checker, which checks whether the gradients that you have implemented for maximum entropy classifier as the max and objective function, if they are correct or not. So if you have implemented it correctly and you run gradient check.sh, you should be able to get very small errors for the non-regularized case as well as the regularized case. Once you have checked that, you would see gradient checks passed as the output. Then you can, once you have implemented the arc-eager parser in its entirety, if you run run.sh, you would be able to see an output like this, which essentially starts by loading training sentences, then extracts the label data, and then after building, encoding, index linearizer, and so on, starts with the iterations. The iterations should go on fairly quickly once the initial computations are done, and that's it for the code. Hope you gain a better understanding of what you need to do based on this, and good luck with your assignment.